thanks ever so much. And like the other speakers, I'd like to say thank you very much to the organisers for putting on a great meeting in a great place. Okay, so this second talk of mine is completely different from the other one before. It's on, I think, an interesting hydrodynamic comparison of structures and interactions of these two glycan antibiotics, vancomycin, teicoplanin. It's a good way of exercising hydrodynamic muscles, which is like what many of us here like to do, depending on which sort of systems our colleagues elsewhere present to us. And this is what Mary presented to us. Okay, these are last line of defense. That means they're used when all other antibiotics fail due to resistance and other things. But these also have problems because bugs are getting clever to these. Right, so how can hydrodynamics contribute to this? Right, these are small glycan antibiotics, meaning they've got sugars on them. That's vancomycin, 1459 Daltons, vancomycin with interesting methyl groups, and looks like a amine group there, glucose. And teicoplanin also has carbohydrates. You know there's carbohydrates there in these ring structures, but you look for ring oxygens. When you've got ring oxygen, that means you've got a carbohydrate residue. But teicoplanin has also got these acyl lipid groups as well. So it's a lipoglycan in that sense. And they have different properties which can impact on their functionality, but they have similar reaction mechanisms. They both attack, again, watch it here because I'm in the presence of expert microbiologists, so they both attack the peptidoglycan membranes of gram-positive bacteria, and they look for these N-acetyl diala residues near the C-terminus end, and there's numbers of bonding opportunities there on the vancomycin and teicoplanin molecules. Of course, this is linked with antimicrobial resistance to these because there's sensors on the membrane of the bacteria which can recognize this and then can induce a mutation in the sequence, which is no longer, we've got DLAC here, no longer recognized by vancomycin and teicoplanin. So this is the plan here. Vancomycin dimerization, vancomycin effects on the VAN-S receptor. We said a bit of this in a previous meeting, I think that Mary gave the talk. But also on teicoplanin assembly and also interactions with mucins, which is of relevance to oral forms of these antibiotics, which are normally given intravenously or subcutaneously. Right, so this molecule, 1459 Daltons, some may argue otherwise, but in our opinion, it's a bit too small to follow by sedimentation velocity unless you run the autocentrifuge to the limits, which we don't like to do. So we can use sedimentation equilibrium. Actually, it's nice today hearing sedimentation equilibrium experiments been done by 2 or 3 speakers. And aren't those patterns beautiful, don't you think? You don't see these in papers anymore, these real optical patterns. There's another one down there that was taken with an old Model E. So we analysed our molecular weight data using SetFit M-star, which uses this M-star function. And all those people who've gone through my lab as PhD students and things have had to use this at some stage, right, all? Right. In fact, with some enthusiasm, because the algorithm for this started off one of those desktop calculators when I was a postdoc with Mike Creeth. And then it progressed to Fortran, like everything else, in the 1990s. And then Helmer came along when he was a postdoc and wrote it in Quick Basic that people could actually understand. In those days, only the programmer with Fortran could understand the program he wrote, right? But with Quick Basic, thanks to Helmut. And then, of course, Peter came along with this SedFit and with ideas which we listened to, and so it was incorporated into SedFit MSTAR. Okay, so it's based on an integral function, so it converts the concentration distribution to what's called an operational molecular weight average called the M-star, which works along the concentration data, rather like the Pac-Man computer game. And by the time it's worked the right way through and got to the base of the cell, it's got the weight average molecular weight over the whole distribution. So it's a nice way of doing it. It's particularly useful for very polydispersed systems because it's an easier extrapolation to the cell base compared to concentration extrapolations, but it still works for small things like these. And then the routine has also got other things. It plots point weight average molecular weight against concentration. And then you can follow the trend in molecular weight. It's noisy because it involves derivative of the log concentration distance squared plot. But at the hinge point, which is the concentration which equals the original loading concentration, that value gives us a check on the M-star estimate for the whole distribution molecular weight. And usually they agree. Right. Yeah, done that, haven't I? I'm going back here. Why is that? Okay, right. So that example is for experiment on vancomycin in 0.9% NaCl, which is the clinical formulation which is delivered to patients. It's actually at 5 mg per mil, but by the time it reaches serum concentrations, it's something like 0.2. It's very low, actually. Is it 2 microgram per mil or 0.2? Not sure. But we looked at a series of different solvents to see this molecular weight behave. These are plots of whole cell molecular weight averages against concentration in different conditions. And this one was chosen because we did some experiments in the presence of the Van S protein. And that's all the data together. If you do these point average plots at different loading concentrations, this is the Rourke Efantis test I mentioned before for reversibility, then these data sets for each solvent condition should overlap, and you can see with an experimental error they do nicely. So it's a reversible dimerization system, and you can fit the Kegelis-Rao equation to estimate the dissociation, the dimerization constant, which you can convert to molar dissociation constant. So you've got a fairly weak dimerization. These plots here. Right, so this is a dimerizing system, and then we looked at the interactions with the Van S, which is involved with the resistance mechanism of the bugs. And okay, it's a membrane protein, but fortunately the membrane domain is quite small. So it's got significant cytoplasmic domains, which means we can dissolve it in aqueous solvents. I know this is only half the story, and we should look at it as well in detergent. But there was still some detergent left over from the purification from the membrane, so that satisfies things a bit. Anyway, we've looked at it in aqueous solution, because the catalytic domain is hydrophilic. Its monomeric value is about 46,000 molecular weight for mass spec. So what do we get from sedimentation equilibrium? And we get the same value, either with the M-star method or with the hinge point method. So it's a monomer. And we can use another program. This was developed with Arthur Rowe, who Jack mentioned before, called Multisig, where you model the profiles in terms of a 17-component system. So you can get a quasi molecular weight distribution. And again, this agrees with the M-star value. So it's still a monomer. Now, with sedimentation velocity of Van S and Van S in the presence of vancomycin, this gets interesting. Again, this is in aqueous solvent. So the black profile is Van S by itself, with noticeably a low sedimentation coefficient. And this was mentioned before, actually, low S values for a given molecular weight. This implies that Van S is very extended. So its S value after conversion is 25, W value is 2.3. And using the molecular weight, you get a very asymmetric molecule. Using ellipse 1, dating from Helmut's time, there we are, Harding, Culfin, and as is Harding, Culfin, and Horton. So approximately a 12-to-1 elongated protein, if those values are correct. Now, when you, that's consistent with the, it's a transmembrane protein, so you'd expect it to be elongated. Now, in the presence of vancomycin, the S value increases to 3 Svedberg. So this is a 30% increase at the same concentration. So the question is this 30% shift due to dimerization or conformation change? There's insufficient mass on the vancomycin itself to noticeably shift the sedimentation coefficient by that much. So is it due to dimerization or conformation change? So again, we check with sedimentation equilibrium, and Van S is still a monomer under these solvent conditions. Again, I stress that. So if that's the case, then the shift in S must be due to a conformation change. And so it shifts actually with ellipse 1 to a much more compact molecule, which apparently is consistent with its with its function. So that's as far as we got with Van S. We didn't explore the solution in detergent conditions. That still needs to be done. We went off on a different pathway, as you'll see in a minute. Now, teicoplanin is a bit different. Again, it's the same sort of molecular weight, but it's got these acyl groups, large enough to look at in DLS, and you can see the shift with change in concentration, which this looks interesting. And the sedimentation coefficient also shows this shift. You can't see this because of the large scale we use looking for large aggregates. But if you plot the S value against concentration, you'll see this sort of characteristic increase and decrease following non-RDRT, whether it was following the Harding rule or something else, I don't know. And then in guanidine hydrochloride, of course, which breaks hydrophobic and also ionic bonds, there's a dramatic drop down to what would correspond to monomeric conditions. And then same sort of thing with sedimentation equilibrium, with M-star analysis. And this is consistent, very different from vancomycin, with an 18, 19-mer assembly, depending on what these higher values are up here. So that was very interesting and confirmed similar observations from what other people had claimed before. Again, this follows on nicely some of the talks before, because VS over V bar has already been, thank you, Patrick, well explained. So using different plausible values for VS over V bar, we explored the possible shapes of the assembly, and again, we just didn't know from that. It could be a highly hydrated VSV bar 2 with spherical, or it could have been 2-4. So we were rather stuck here. So to get a unique estimate, we use Jose's single hide fit, which is quite useful. You feed in the, and I'll explain this tomorrow, intrinsic viscosity, S value, Stokes radius from DLS, and along with molecular weight and V-bar data. And you use this minimization function. It's an adaptation of hide fit, which is for when you've got large data sets of intrinsic viscosity, molecular weight, sedimentation coefficient, molecular weight, RG, molecular weight, fitting the various routines, Bodanecki, Yamakawa, Fuji, and things to work out things like persistence lengths and mass per unit lengths. But in this case, it's worked out an actual ratio for us of 1. So it is a sphere, which sits nicely on the ellipse plot. So there we go. And most of these large blob-like molecules are spheres. Right, just to finish off, vancomycin and teicoplanin are mainly delivered intravenously, but there are formulations that can be delivered orally, ocularly, or nasally. And this means they have to come into contact with one of my favorite molecules over the years, and that's mucins, mucus glycoproteins. That was my time with Michael Creeth all those years ago. And these are very highly hydrated, large structures, heavily glycosylated, about 80%, and with an overall swollen domain with high hydration. But the sugars are interesting because they contain things like fucose, sialic acid, characteristic regions for interactions. And if anyone has any doubt how important these sugars are, then you should look at Carolyn Bertozzi's excellent Nobel Prize lecture from 2022. It really is brilliant on how all these things link with. Some people have already seen it. They're not nodding their head. It is great, isn't it? Right, so what happens here? And this came from a project student. Haley, we had project students, shouldn't say this really. I won't play this back to my project students. But sometimes you're a bit stuck for what they could do. So we had some mucin in the fridge, and we had some vancomycin in the fridge. Let's just put the two together and see what happens. And then at 3,000 RPM, you saw this huge peak, huge sedimentation coefficients, peak going down, and it was concentration dependent. So at lower concentrations of vancomycin, you didn't get such a great effect. Because by the time you sped the whole thing up to 45,000 RPM, there was no mucin left because it had all been taken down by the interaction with the vancomycin to form very, very large complexes. I was with pig gastric mucin. The same effect with pig intestinal mucin. Again, a clear out. And with bovine submaxillary mucin, not quite as much as a clear out. There's still some mucin still showing at 45,000, but submaxillary mucins have a lower carbohydrate content, 50% instead of 80%, so that might explain that. Again, verified by DLS. You all heard about orthogonal techniques. So there's the complex there with pig intestinal mucin. And also we see this under SEM, environmental SCM, which allows you temporarily to image these things in the presence of liquid. And these huge 20 micron complexes, which actually correspond, if you work out what the size is from those 3,000, 4,000 sedimentation coefficients, and I was pushing things right to the limit, then it agrees with things of this size. Again, for pig intestinal mucin, that was PGM before, and smaller ones for bovine submaxillary mucin. And then when we tried teicoplanin, we got similar effects with these as well. And this has all been published. So this is quite exciting, showing that these techniques all agree. And a mechanism for how this thing might work and was relevant is that maybe electrostatic complexes of mucins with the vancomycin forms this mesh, which basically traps the bugs in, while the vancomycin chomps its way, or teicoplanin chomps away, and does it work? So it actually aids the oral function, or nasal or ocular function of these things. So that's basically it. Thanks to, again, a large number of people, particularly Taiwu Chun and Yudong, the PhD students, Haley Zer, UCLan, it was actually her project, working with Ryan Lithgow on the mucins. And once again, to Helmut for providing or helping with the background stuff behind all this. And with that, I'll stop. Thank you.